So the usefulness of the large margin classifier that we developed in the previous section of the lecture is significantly reduced because it requires the data to be linearly separable. This is known as a hard margin classifier. It insists that the margin is achieved or else it can't fit at all. What we're going to do now is attempt to soften that margin, allowing us to fit non-linearly separable data. In other words, we want to allow some of the classifications produced by our decision boundary to be wrong. We obviously don't want that to be the norm. We want to be able to penalize the fact that we're getting things wrong, but we do want to be able to do it because sometimes there's just no choice. The way that we do this is by introducing what are known as slack variables into the optimization. These are variables that allow a certain amount of leeway in which margin is chosen. They provide the optimizer with the option of trading off margins that are too small or even on the wrong side completely in order to get a better fit overall. There's one of these training samples which are known as Xi or Z, I'm going to say Xi. There's one of them for each of the training samples. So it is a measure of how much slack has been taken up by that sample. And then we impose a limit on the total amount of slack that can be consumed. So the optimizer has a budget for errors that it can spend if it needs to, but it's a limited budget. We can pose this as a maximization problem, very similar to the margin maximization we used before, but with these additional constraints. We're now maximizing over W, B, and all of the Xi, and we're still maximizing M, subject to the margin constraint, but with a degree of slackness in the margin constraint, but then additional constraints on the Xi themselves. As in the hard margin case, this is not a solvable problem as it stands, but we can similarly rearrange it to get rid of the M and rephrase it only in terms of W and B and Xi. In this minimization, we're still attempting to minimize the squared magnitude of W, but in addition, we're minimizing the total sum of the slack variables with some governing coefficient C, which is known as the cost. Our constraints are now that the margin has to be bigger than or equal to 1 minus the slack, and the slack variables all have to be greater than or equal to 0 in order that the optimizer can't trade off big distances away from the margin for big errors on the wrong side of it. When we form the Lagrange multiplier primal objective for this problem, the structure is very similar to how it was for the hard margin case, but now it's a bit longer and more complicated, and we have two distinct sets of Lagrange multipliers. There is the alpha, which control the margin constraints, and also there are now these mu I, which control the constraints on the slack variables. When we differentiate this expression in the same way as before, substitute in order to form the dual objective, we get something which looks exactly the same as in the hard margin case in terms of the objective function itself, but with additional constraints. In particular, the constraint that all of the alpha I can be no larger than the cost coefficient C. The KKT conditions here also include the slack variables. We get these conditions here. What this amounts to is that the alpha I are no longer 0 just on the margin itself, but also for any points that are within the margin. When we look at this formulation, the same properties that we saw in the hard margin case continue to hold. W is still a weighted sum of a subset of the training examples. The inputs only enter into the classifier both at fitting time and at prediction time in the form of pairwise inner products between individual samples. And again, many of the coefficients alpha will be 0. However, there are likely to be more that are non-zero because they account not only for the ones literally on the margins, but also for all of the other failure points. So there are potentially a lot more support vectors. This cost parameter C in the optimization actually looks a lot like the lambda coefficient for the penalty term in regularized regression expressions like for ridge regression and for lasso. And in fact, it serves a very similar purpose in trading off the two different objectives. This softening of the margin, the relaxation of the hard margin constraint, can be viewed as a form of regularization. C imposes an upper bound on the coefficients alpha. As such, it stops the optimizer from paying too much attention to any individual sample. In doing so, it can help reduce the susceptibility to outliers. If C is very high, the optimizer can still pay a lot of attention to individual samples. The worst case examples have a lot of potential influence, and so the fitting will be subject to overfitting. If C is very low, then the contribution from any individual sample is capped at a pretty low level, and so more of a consensus fit will be performed. This could potentially encourage underfitting. One thing to note is that lambda for lasso and ridge and C for this soft margin classification operate in opposite directions. So a large C is equivalent to a small lambda. We can also conceptualize this soft margin maximization as a loss minimization problem which can be solved by gradient descent. The loss function in this case is known as the Hinge loss, and it looks like this. Here's a plot of it compared to a 0, 1 loss. It's not differentiable at the hinge point, at the margin of 1, but otherwise it is, and you can generate a subgradient, and then the loss is convex and optimizable by gradient descent. So solving the soft margin problem as a quadratic programming problem and solving the hinge loss optimization by gradient descent are more or less equivalent. If we combine a hinge loss minimization with a regularization penalty, ridge regression style on the weights term, then this is really just a rearrangement of the soft margin optimization problem. The slack variables correspond to the hinge loss component, and the L2 penalty on W will serve as the minimizer of the weights, which is the same as the original objective in both the hard margin and soft margin cases. In certain cases, solving the hinge loss minimization by gradient descent or related methods can be more tractable than the QP problem required to solve the full soft margin problem. However, minimizing the hinge loss does not produce a solution in which the inputs enter only via pairwise inner products. We'll see why that's important in the next section.